Excellent. The cookie order exercise showed us a basic inheritance relationship and how polymorphism allows specific behavior via overridden properties. For our next problem, we'll explore a richer inheritance hierarchy with geometric shapes like rectangles, squares, and triangles. This problem introduces the idea of an abstract base class, geometric figure, which provides a common definition but isn't a complete shape on its own. We'll see how abstract methods in the base class define actions that all shapes must be able to perform, but leave the how to the specific shape class. This is key to designing flexible systems where different shapes can be handled uniformly. Now we move to problem 2, the shapes demo. This problem is a classic example of using abstract classes and implementing polymorphism in an inheritance hierarchy. We need an application shapes demo and classes for geometric figures. Geometric figure is the base class, but it's defined as abstract. Abstract classes. Abstract classes cannot be instantiated directly. They serve as blueprints for derived classes and can contain both concrete members and abstract members. Geometric figure includes properties for height, width, and a read-only area. It must include an abstract method called compute area. Abstract methods. An abstract method has no implementation body in the abstract class. It must be implemented, overridden, by any non-abstract class that inherits from it. This defines a required behavior for all concrete descendants without specifying how that behavior is carried out in the base class. We need 3 derived classes, rectangle, square, and triangle. Rectangle inherits from geometric figure and implements compute area as width times height. Square inherits from rectangle. It needs constructors to ensure width and height are always equal. It should use the rectangle's compute area method. This means square itself won't override compute area again. It will inherit the overridden version from rectangle. Triangle inherits directly from geometric figure and implements its compute area as width times half height. The shapes demo application should create objects of these derived classes and pass them to a single method that accepts a geometric figure argument to display their data. Changing dimensions and redisplaying should show recalculation. Let's look at the abstract base class geometric figure. Abstract class geometric figure. It cannot be instantiated. Fields. Protected in height, width, and area. Protected allows derived classes access. Constructor. A constructor that takes height and width and assigns them using the properties. Abstract method. Public abstract void compute area. Abstract method. This method is abstract. Geometric figure doesn't know how to compute the area. A rectangle, square, and triangle do it differently. By declaring it abstract, we force every concrete derived class to provide its own implementation. This is a powerful way to define an interface for behavior. Virtual properties. Public virtual int height and public virtual int width. Virtual properties. These properties are marked virtual, allowing derived classes to override their getters or setters. Notice that the setters call compute area after setting the dimension. This is important. Whenever a dimension changes, the area is automatically recalculated by calling the compute area method. Which compute area method gets called? The one belonging to the actual type of the object at runtime. That's polymorphism. Read-only area property. The read-only area property ensuring the calculated area cannot be modified externally. Here's the rectangle class, inheritance. Class rectangle : geometric figure. It inherits from the abstract base class. Constructor. The constructor using base HW to call the base geometric figure constructor. This sets the height and width and thanks to the base class property setters calls compute area. Implementing abstract method. Public override void compute area. Abstract method polymorphism. This method provides the concrete implementation for the abstract compute area method declared in the base class. It calculates the area specifically for a rectangle, area equal width times height. This is polymorphism. The compute area call defined in the base property setter will now execute this specific code when called on a rectangle object. The square class on shows multi-level inheritance and property overriding. Inheritance. Class square : rectangle. Square inherits from rectangle, which inherits from geometric figure. Square therefore inherits width, height, area, and the overridden compute area method from rectangle. Constructors. The 2 constructors for square, both using base WW or base WH. The key here is that they pass the same value for both height and width to the base rectangle constructor, fulfilling the requirement that squares have equal sides upon creation. Property overrides. Public new int height and public new int width property overriding. These new property implementations ensure that when the height or width of a square is set, the other dimension is automatically updated to match it, maintaining the square shape. Calling base logic. Importantly, within these setters, they still call compute area. Since square inherited the rectangle's overridden compute area, this call will execute the rectangle area calculation, width times height, which is correct for a square since width and height are kept equal. Maneuvers override. The use of new here hides the virtual properties from geometric figure. If height and width in geometric figure were abstract properties, square would use override. The new keyword is used when hiding a virtual or non-virtual base member. The triangle class demonstrates implementing the abstract method directly from the base, inheritance. Class triangle : geometric figure. It inherits directly from the abstract base, constructor, the constructor calling base HW. Implementing abstract method, public override void compute area, implementing abstract method. This method provides the specific implementation for the abstract compute area method for a triangle, area equal width times height, over 2. When compute area is called polymorphically on a triangle object from the base class property setters, this code will run. Finally, let's see the Shapes demo application in action. Object creation. Create objects of rectangle, square, and triangle, demonstrating their constructors. Polymorphism with display method. Look at the display shape statistics method. Static void display shape statistics geometric figure G. Abstract base type reference. This method accepts an argument of the abstract base type geometric figure. This is the power of polymorphism. We can pass any object that is a geometric figure, i.e., any object of a class that inherits from geometric figure, like rectangle, square, or triangle, to this single method. Crucially, when dimensions are changed and the object is passed back to display shape statistics, the property setters, which called compute area, and the subsequent access to the area property demonstrate that the correct type-specific compute area method was executed polymorphically. The method doesn't need to know if it's displaying a rectangle, square, or triangle. It just calls the method's properties defined on the base class, and the correct behavior for the specific object type is executed. Runtime behavior. Inside the display shape statistics method, it accesses properties like G height, G width, and G area. Even though G is a geometric figure reference, when this code runs, the properties of the object's actual runtime type, rectangle, square, or triangle, are accessed. In this exercise, we covered significant OOP concepts, abstract classes, and abstract methods to define common interfaces and required behaviors in base classes. We demonstrated inheritance hierarchies with multiple levels. Most importantly, we saw polymorphism in action through method overriding, implementing abstract methods like compute area and overriding toString. Overriding properties in Square, calling base class logic, base, set price, and using base type references, geometric figure in display shape statistics to enable code that works flexibly with objects of different derived types. These principles are fundamental to designing scalable, maintainable, and flexible object-oriented systems. Thank you for joining me for this session.